The following was made as a television videotape. Its purpose is to provide orientation for those teaching the CHEM Study course.
Probably the most useful thing that a teacher has in teaching chemistry, and a most useful thing the student has in learning chemistry, is the periodic table. It relates the elements to one another. It arranges them in family columns, in rows. The trends and properties are fairly uniform up and down the columns, and even across the rows. But there is another device which is almost as useful as the periodic table. This is what we have come to call an energy level chart. We have one of these here, which most of you have seen, and I hope all of you have a chance to use in your classrooms. It is a chart, as you see, with various squares on it, which represent regions of space, orbitals, in which electrons can exist. In addition to the squares, there are some numbers, 1, 2, 3, 4, and so on. These are merely the numbers that we use to describe the orbitals. And these numbers, in connection with the letters, like 1s, 2s, 2p, 3s, 3p, and so on, allow us quickly to describe these squares. Now, if we merely stopped here, we wouldn't have much idea what it was that the orbital chart was supposed to relate. But we notice that over here it says energy increasing. As we move up, these orbitals, these regions in space, have increasingly great energy. An electron in here is at its minimum energy. Now, the reason for this is that we are considering in this chart that the nucleus is down toward the floor and is attracting electrons. We can represent the electrons with these magnets, and the magnets stick to the steel orbital chart. Now, of course, they have to be in the orbital, but if we had only one electron around any given nucleus, we would expect it to fall toward the nucleus through these various regions of space, represented by the squares, to the 1s orbital, the 1s region in space. If we add another electron, like this, it too will go into this region of space. Now we notice one more thing about these electron magnets. They have a black end and a white end. This is intended to represent the property called spin. Electrons in a given orbital have to have their spins pointing in opposite directions. And this is why we have the white end up here and the white end down here. Each orbital then can hold 2 electrons. Now, this is all very simple and very easy. The real question from the standpoint of the students, and indeed from us as teachers, is where did all this evidence come from? Why do we know that there are such orbitals? And how can we use these, other than in a purely mechanical fashion, to tie chemistry together? One such way is to point out that this orbital chart comes from a measurement, among other things, of ionization energies. The ionization energy is the energy required to remove an electron completely from the atom. For example, here we have 2 1s electrons. Were energy to come along and completely remove one of these electrons from the atom, we would say the atom has been ionized. And the energy necessary to remove this electron completely is called the ionization energy. Well, now, of course, it is not only possible for electrons to be in 1s orbitals, they can be in other orbitals as well. We could have them here, because now the 1s is full. No more electrons can go down. If we take an atom with 4 electrons, it will come down until it pairs up in the 2s orbital. Thus, what we have here is a plot, really, of electron energies. These are the electrons that spend a lot of time in regions of space close to the nucleus. These are further out. The 2s orbital is further out. It extends farther into space. The 3p still farther. But again, what about the experimental evidence for this? Well, let's do a very simple experiment to give a little bit of background. Suppose that we light a burner here. This is one of the propane torches available in most hardware stores. And you probably cannot even see the flame on your television screen. But suppose I clap my hands next to it. Can you see the yellow flecks in the flame? The question is, what does clapping my hands have to do with the flame? Well, now, if you were watching very closely, you saw that I rubbed my hands on this eraser. What I'm doing, of course, is putting chalk dust on my hands. And when I clap them next to the flame, the chalk dust leaves my hands and gets into the flame. And when it gets into the flame becomes colored. Yellow spots are seen, particularly out in this region. Well, you might well ask, what in the world has this got to do with ionization energy? Let's go back to our chart for a moment and see. Chalk is mainly calcium sulfate, but almost every chemical compound has some impurities in it containing sodium. And thus, chalk and almost everything else does contain sodium. Sodium in the periodic table is element number 11. In its compounds, sodium is present as Na+, sodium ion, with only 10 electrons. Those 10 electrons would be distributed 2 here, then 1, 2, 3, 4, 5, 6 here. That makes 2, 4, 6, 8, 10. Sodium ion then would have its electrons here, here, and here. In a flame, there are many extra electrons. When one of these outer electrons comes falling in from the flame toward the sodium ion, because of the attraction of plus for minus, energy is emitted. And the particular energy which is emitted when the electron falls from this level to this level is emitted as light. So that we have then the sodium line being emitted when electrons fall in. I think I just pointed to the wrong orbitals. Actually, the sodium light, the yellow light, is when the electron falls from this orbital to this one. How could it have gone to this one when these were already full? Ionization energy, then, is the energy required to remove an electron completely. The light one sees in flames is due to the light which is emitted when electrons fall back in toward the nucleus. In the case of sodium, the yellow line that you are so used to is from here to here. Now, it's difficult to do a lot of experiments on ionization energy in a simple classroom. And therefore, we have prepared a film in collaboration with Professor Bruce Mahan of the University of California, Berkeley, called Ionization Energy. This film will present further experimental evidence on ionization energies and on their interpretation in terms of the periodic table.
This is a CHEM Study film produced by the Chemical Education Material Study for use in its course in chemistry. Here is a piece of metallic sodium in a beaker. In this container, we can warm the sodium and at the same time surround it with chlorine gas. First, the sodium melts. Then, as it vaporizes, the reaction begins. In this reaction between sodium gas and chlorine gas, each sodium atom loses an electron to a chlorine atom, and the ionic substance sodium chloride is produced. In the reaction, a 3s valence electron from each sodium atom has been transferred to a chlorine atom, as shown on these orbital boards. Neon is the element just preceding sodium in the periodic table. It has only 1 electron less. Let's see if neon reacts with chlorine. First, the beaker is filled with neon. Then it is heated, just as we heated the sodium. Moisture condenses on the outside of the beaker at first, but it disappears as the beaker warms. Now, as chlorine gas is added, it can be seen mixing with the hot neon gas. Yet, no reaction occurs. Neon is inert. in contrast to sodium. One of the factors that determines the difference in reactivity between sodium and neon is the ionization energy. In this film, we shall see how ionization energy is measured and how it varies. To show one way in which ionization energy can be measured, let us first work with the element sodium. The ionization energy is the energy required to remove an electron from an isolated atom, and in metallic sodium, the atoms are not isolated. However, when metallic sodium is melted and vaporized, individual isolated sodium atoms are formed in the gas phase. This representation of an isolated neutral sodium atom will help to show what is meant by ionization energy. When a sodium atom absorbs energy, for example from a photon, the single valence electron may be ejected, leaving a sodium ion. This is the process that occurs when we measure ionization energy. Ionization energy, then, is the minimum energy needed to remove an electron from a gaseous atom. The energy needed to ionize the atom can be delivered to the atom in the form of light, heat, or electron bombardment. Here is an experimental device for measuring ionization energy. It consists of a vacuum pump, several reservoir bulbs of gases, and an apparatus in which the electrical conductivity of gases can be measured. Ionization produces an electron and a positive ion from a neutral atom. Thus, the electrical conductivity of any gas present will show a sharp increase when ionization occurs. The cell, which is placed in an oven, contains 2 electrodes so that the electrical conductivity of any gas between them can be measured. The wires through the cell walls connect the electrodes to a battery so that an electrical current flows when ions are formed in the gas. The meter in the circuit indicates the amount of electrical conductivity. This meter is so sensitive that it will even detect the extremely low conductivity of distilled water. As sensitive as this meter is, we are still unable to detect any conductivity in the empty cell. If a gas is placed in the cell and the meter shows that current is flowing, it is due to ionization of the gas. For this experiment, the source of energy used to ionize the gas will be light from a mercury lamp. The light is directed by a series of mirrors through a quartz prism. Then it enters the cell, where it may be absorbed by gas atoms to form ions. All the light that enters the cell must pass through this slit, which admits only a single frequency at a time. Now let's cover the lamp, turn it on, and see how the instrument works. The light passes through the prism, which separates it into different colors. Each color of light has a characteristic frequency which determines the energy. The slit admits a particular frequency to the cell. Now we have placed the cover on the instrument. The micrometer head, which controls the quartz prism, allows us to select a single frequency or color to pass out through the slit and enter the cell. Green light has a frequency of about 7 times 10 to the 14th cycles per second. As the color changes from green through yellow to red, the frequency decreases to about 5 times 10 to the 14th cycles per second, and a correspondingly lower energy. Turning the micrometer head the other way, we go from red to violet, and then, continuing to still higher frequency settings, ultraviolet light comes from the instrument, but our eyes don't respond to it. We can find the energy of any particular color of light by multiplying its frequency, nu, by the conversion factor, h, Planck's constant. Now let's proceed with the experiment. There's sodium here in the side arm of the cell, so that when the oven surrounding it heats, sodium vapor will fill the cell. In order to make our measurements on pure gaseous sodium, we must first open this stopcock and pump all the other gases from the cell. This gauge shows the pressure in the cell. For our experiment, the pressure must be less than 1 micron, less than a millionth of an atmosphere. Now we have a good vacuum, so we'll turn on the oven and heat the cell. As soon as the sodium starts to vaporize, we will seal off the cell. The sodium melts, and when it strikes the hot glass, it boils. Light of a known energy shines through the oven and cell windows and into the gas. We'll begin with low energy red light. Watch the meter while we slowly increase the frequency of light entering the sample. There, the meter reading becomes large, indicating a large increase in the conductivity of the gas. The high-energy ultraviolet light has ionized the sodium. Let's go back and measure the lowest frequency which first causes ionization. Let's increase the frequency slowly and watch the meter more carefully this time. There, the conductivity rises rapidly. The micrometer reading corresponds to an ultraviolet frequency of 12.4 times 10 to the 14th cycles per second. Let's consider this diagram to understand what happened. The high-energy light photons ionize the sodium atoms. The electrons which are released go to the positive electrode, and the sodium ions move to the negative electrode. Electrons flow, and conductivity becomes appreciable. Now let's take a look at this process on the molecular level. A sodium atom absorbs a photon, and almost immediately an electron is ejected. The resulting charged particles then move under the influence of the electrodes. This process is called photoionization. A sodium gas atom plus a photon gives a sodium gas ion plus 1 electron. With this equation, we can calculate the ionization energy of sodium. We have determined that nu equals 12.4 times 10 to the 14th cycles per second in this equation. Now, multiplying by the conversion factor, H, 9.53 times 10 to the minus 14 kilocalorie second per mole, we find the ionization energy of sodium is 118 kilocalories per mole. Considering the simple apparatus which we have used, this value compares well with the accepted value of 118.4 kilocalories per mole. We have demonstrated that one of the ways to measure ionization energies is to use photons to provide the energy for ionization. Another way is through bombardment with fast-moving electrons. This alternate method permits us to check our earlier result, and it can readily give much higher energies. In this cell, we generate electrons and make them move very rapidly by strong electrical forces that can be easily controlled. A diagram will help clarify the experiment. Again, a circuit of 2 electrodes with a battery and meter will be used to detect current, hence the presence of ions. In order to obtain fast electrons as our source of energy, we first add a filament to the cell. The filament is connected to a battery. The filament heats and emits electrons from its surface. There is a metal screen through which most of the electrons can pass. It is called a grid. The grid is connected to a source of positive voltage which attracts the negative electrons. The energy of the electrons is controlled by the value of the positive accelerating voltage. Knowing the voltage allows us to calculate the energy of the electrons. As the accelerating voltage is increased, the electrons are given more and more energy. Note the similarity to the previous experiment, except that instead of photons, electrons pass through the cell. When the bombarding electrons acquire high enough energy, their collisions with gaseous sodium atoms produce ions, and the conductivity of the cell rises, as shown by the meter on the left. Now let's proceed with the experiment. Once again, all other gases must be removed from the cell. Again, we'll use the vacuum pump. The gauge shows that there is a good vacuum. When the cell reaches a temperature sufficient to vaporize the sodium, we can begin. Now we're all set. As the accelerating voltage is increased, the bombarding electrons carry more and more energy. Very little current flows through the sodium vapor, as shown by the ammeter on the left, until the voltage reaches a critical value. Then the current shows a rapid rise. Let's repeat, this time carefully reading the accelerating voltage at which a large increase in the current occurs. These random fluctuations are not meaningful. There, ions are now being produced. The voltage meter reads 5 volts. On the molecular level, an electron with sufficient energy ionizes a sodium atom, producing a second electron and a positive sodium ion. The sodium ion is attracted to the negative electrode, and the electrons are attracted to the positive electrode. The process of exciting a sodium atom so it can eject a 3s electron is represented by this equation. The energy comes from the bombarding electron, shown on the left. The ionization energy of sodium can be calculated from the measured accelerating voltage of 5 volts. An energy of 5 electron volts was given to each electron. We can change the units to kilocalories by multiplying by the factor 23.1. Thus we obtain about 115 kilocalories per mole with an uncertainty of about plus or minus 10. This is good agreement with the value determined by the photoionization method, 118. Now let's use this electron bombardment method to measure the ionization energies of some inert gases. In these bulbs, we have samples of 3 of the inert gases. Through this tubing, we can fill our cell with any one of these 3 gases. Let's start with helium. The cell is already empty, so we can now admit our sample. Helium is a gas at room temperature, so we don't need to heat it. It takes a voltage considerably higher than that for sodium to cause the ionization process to begin. Now watch the meter on the left. There. This sudden large rise indicates that ionization has occurred. The reading is about 25 volts, nearly 5 times the value for sodium. This value is in reasonable agreement with the value we find in a reference book, 24.6 volts. This more precise value gives an ionization energy of 567 kilocalories per mole. Now let's take the next gas, argon. The helium has been pumped out of the cell and argon added. We proceed as before. There we go. Ionization begins. The reading is about 16.5 volts when ionization occurs. The accepted value is 15.8 volts, which corresponds to 363 kilocalories per mole. Now let's try the third gas. The argon has been removed, so xenon can be added to the empty cell. Now we're ready to measure its ionization energy. The reading is about 12.5 volts this time. The accepted value is 12.1 volts, which corresponds to 280 kilocalories per mole. From the book, we've added the ionization energies of krypton and neon to our list. We see now how the ionization energies are related to the atomic numbers. The values are all high. Remember, the value for sodium was only 118. Let's plot these ionization energies against atomic number and observe the trends as related to the periodic table. Helium, with atomic number 2, has an ionization energy of 567 kcal per mole. It goes here. In a similar fashion, we can plot the rest of the inert gases in our table. We can see from this plot that the ionization energies of the inert gases decrease with increase of atomic number. The ionization energy of the alkali metals can be added to our plot. Lithium, sodium, and the others. The ionization energies of the alkali metal group are all much lower than those of the inert gases, and they decrease very slowly with increasing atomic number. With this same chart, we can show the ionization energies of many elements. Within a given row of the periodic table, the ionization energy tends to rise as the atomic number increases. This characteristic trend is repeated in each row, the same sort of repetition we find in the chemical properties that give rise to the families of elements. We shall find that the ionization energy aids us in explaining the existence of these families. Ionization energy, then, is the minimum energy needed to remove an electron from a gaseous atom. We have explored two measurement techniques: photoionization electron bombardment. We have compared the ionization energies of the inert gases to those of the alkali metals. We have indicated how, across each row of the periodic table, the ionization energies regularly increase, forming a pattern which not only helps us explain the regular trend in chemistry from element to element, but it helps us understand the very existence of the periodic table.